Hey everyone. So this is our last lesson of Unit 1 for calculus, and it's on infinite series. Now we're going to accomplish a couple of things here. Part of this lesson is to take a look at horizontal asymptotes again, and we're going to look at calculating horizontal asymptotes from a calculus perspective. So in 30-1, there's a couple things we did with horizontal asymptotes. We either said, hey, just remember these three scenarios where, if you have a bigger degree on the top or a bigger degree on the bottom or same degree over same degree. The other thing maybe a teacher once told you is just to put a really big number in for x and see what happens, because that's essentially what happens as x approaches infinity, right? Infinity is really, really big. So if you just, plug a million in for x and take a look at what's happening, that might give you a good visual. Remember, I think yesterday I talked about the fact that part of calculus is trying to look at things we already know, but from a calculus lens. And so what I want to do today is take a look at how would we algebraically figure out the horizontal asymptotes. So how do we look at horizontal asymptotes from a calculus lens? Okay. The other thing we want to do by the end of this note, in 20-1, you were introduced to sequences in series, and we talked about arithmetic and geometric sequences in series. And then at the very end of that unit, you were given a formula for you were given a formula for the summation of an infinite series. And what I want to do with you by the end of today is actually develop that formula with you so that you can see it actually comes from a calculus perspective. It's not just something somebody made up and said, here, use this, okay? All right, so let's get started. Just as a quick reminder, a geometric sequence is a list of numbers such that there's a common ratio between every pair of successive terms. So you're multiplying each term by the same amount each time, okay? So 2, 4, 8, 16, if I went through that sequence, I'm multiplying by 2 every time. So my common ratio would be 2. Now, a series is the sum of a given number of consecutive terms in a sequence, okay? So where the sequence is just the terms, if I start adding all those terms together, now I would have a sum. So consider 1, 2, 4, 8, 16, 32, 64. You can see my common ratio there is 2. I'm multiplying by 2 every time. And then if I wanted to look at it as a series, I'd be looking at the bottom guy. Now I'm saying 1 plus 2 plus 4 plus 8, and so on and so forth. Okay, so we're going to take a look at a couple here. The general term of a particular infinite sequence is defined as T of n equals n over n plus 1. Determine the first 5 terms in the sequence, okay? Not very complicated. We're going to plug 1 in for n, see what we get out. We're going to plug 2 in for n, see what we get out. Go ahead and do that. Okay, and so your 5 terms should have ended up being 1/3, 1/2, 3/5, 2/3 when reduced, and 5/7. Okay. Okay, now what I would like you to do is to plot this. So you've got 1, 1/3, 2, 1/2, 3, 3/5. Okay, go ahead and plot that on a grid. Okay, and you should be looking at something like this. Now, question, explain whether or not T of 90 or T of 9,000 will be greater than or equal to 1. And the answer is no. You'll never be greater than or equal to 1 because you're always putting 2 more on the bottom than whatever n is, okay? So you would always end up with a number on the bottom larger than the number on the top, so it would be a fraction less than 1. Now, as these numbers get big and big and big, you guys are brilliant already, right? You can see that that means, hey, I'm going to be approaching 1 here, which means I have a horizontal asymptote at 1, okay? But we'll dive into that more in just one sec. Okay? Okay, so here is just one sec. Determine the limit as n approaches infinity. So now take a look at this, because I know some of you asked questions on this when we were just introducing limits. N is not approaching a number anymore. When n is approaching infinity, then we're trying to decide, this is where we often decide whether we have a horizontal asymptote or not, okay? Because when n approaches infinity, when n approaches a really, really large number, you know, there's not a whole lot that could happen. Either y is going to increase or decrease without bounds, so it's going to be going up and up and up and up, or it's going to be going down and down and down and down. In that case, there would be no horizontal asymptote. Or what's going to happen is the y values approach a particular number, okay? Now, let's have a little calculus perspective here for a second. If I want to determine the limit approaching infinity, what we do algebraically, and this is what I would expect from you in your work, is we divide everything by the highest power in the denominator, okay? After that, you think about what happens when we put large numbers in for n. So take a look at this. My denominator is n plus 2, so the highest power is n there, it's n to the 1, okay? So I'm going to divide every term I see by n. That's going to look like this. So the top included, okay, n divided by n divided by n, and 2 divided by n. Now what that gives me is 1 over 1 plus 2 to the n. Now, take a look at this guy for a sec. Oops, sorry, I'm just trying to get my ink back on. I don't know where my ink went. There it is. You guys, I know that sounds crazy on your perspective because you guys don't see all the little boxes that are on top of my PowerPoint right now. You only see the finished product, but there's boxes everywhere on top of my PowerPoint. Okay, so take a look at this guy for a sec. If I put a really big number in for n there, I get, like, think about a billion. 2 divided by a billion. 2 divided by a billion is essentially going to be pretty close to 0, okay? So what happens is, as n approaches infinity, that number approaches 0. And so the limit becomes 1 over 1 plus 0, okay? And then that would just be 1 over 1. Okay, so we now know as n approaches infinity, the limit is 1. Okay, that tells me I have a horizontal asymptote at y equals 1. Okay, so now we're looking at horizontal asymptotes from the lens of calculus instead of just memorizing a table like we did in 30-1. Okay, let's try another one. The general term of a particular infinite sequence is defined as t of n equals 1 over n squared. Determine the first 5 terms in the sequence. So again, you're going to plug 1 in for n, 2 in for n, 3 in for n, 4 in for n, 5 in for n. We will get 1, 1/4, 1/9, 1/16, and 1/25. Okay? Go ahead and graph that for me. Okay, once you've graphed it, you should get a picture that looks something like this. Okay, and we can see kind of this decaying exponential graph. And what am I approaching? Well, visually, oh, sorry, I didn't mean to do that yet. Visually, you can see I'm approaching the line y equals 0. Okay, but now we want to look at that from a calculus perspective and decide how I would algebraically determine that. So we want to determine the limit of 1 over n squared as n approaches infinity. Now remember, we're going to take the highest degree that we see on the denominator. So that is an n squared. I'm going to divide everything by n squared. 1 over n squared over n squared over n squared then. That essentially becomes 0 over 1. Okay, this guy here, just switching colors here. This guy here becomes 0 and that guy there becomes 1. Okay, 0 divided by 1 is 0, so the limit is 0. So as n approaches infinity, algebraically, we have determined that the limit will be 0. Okay, and we saw that visually just on the previous slide. Okay, so in general, things you want to understand. The limit of 1 over n to the anything will become 0 as n approaches infinity, as long as r is greater than 0. Okay, so the limit of 1 over n to the anything, n to the r, will give me 0 as n approaches infinity when r is greater than 0. Okay, so using that property, let's go ahead and just practice a few limits here, okay? So determine the limit as n approaches infinity of n over n plus 1. The highest degree I see on the denominator is the n, so everything gets divided by n, and I'm left with 1 over 1 plus 1 over n. This becomes 0. I'll just circle that again for you so you can see where I am. Okay, that will become 0 because of that property. And so the limit here will be 1 over 1, which is 1. Okay. Okay, the limit of n squared minus n all over 2n squared plus 1, where n approaches infinity. Again, I will divide everything by n squared because that's the highest degree I see on the denominator. So when I divide everything by n squared, I'm looking like this first. This is going to be a 1. This is going to be a 1 over n. This guy will be a 2, and this guy will be a 0, essentially. Okay, so both of these guys will move to 0, and I'll be left with 1 over 2. Okay, now, again, some of you are saying, Hill, why would I ever do this when you taught me in 30-1 that when I have the same degree over the same degree, I just take leading coefficient divided by leading coefficient? You're right, but you're not communicating from a calculus perspective, okay? This communicates from a calculus perspective what that horizontal asymptote is, okay? And so yes, this is what I need to see if you are asked to determine these types of limits, okay? All right, using the property, determine the following: the root of n over n minus 3 as n approaches infinity. Okay, so the highest I see, the highest degree I see is 1 for the denominator. So I'm going to divide everything by n. Okay, and that'll look like this. Okay, so now I end up with 0 over 1 minus 0. Okay. And that's going to end up being 0 over 1, which is 0. I was hesitating there, partly because I'm just, when doing videos, I'm trying to think what's going to bother you in this video. Let's just unpack this guy for a sec. So that's going to be 1 n to the 1/2 over n, right? The square root of n is n to the 1/2. Okay. So the larger degree is still on the bottom here, which means think like put 10 million in there for a second. The square root of 10 million over 10 million, that's still going to approach 0, right? Compare that to the square root of 1 billion over 1 billion. Okay. Okay. Give this guy a try. Now, I can see right away that the highest exponent in the denominator is n to the 4. So everything gets divided by n to the 4. I need to see this in your communication, okay? Okay, so this is going to simplify. Oh, my animation's off. Oh, spoiler alert, the answer is 0. But that's okay. So this simplifies to 1 over n plus 5 over n cubed. And then I've got a 2 minus 1 over n plus 1 over n to the 4. This is going to be a 0. 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 So I end up with 0 over 2, which is 0. Okay. All right. Good job, guys. Okay, take a look at this guy now. The limit of 1/2 to the n, where n approaches infinity. Okay. Now, this one's a little different because it's not an n to the something, it's a something to the n. Okay, so n is no longer my base, it's my exponent. So let's take a look. 1 to the n is 1, right? 1 to the anything is going to be 1. But then I've got 2 to the n on the bottom. So think about this. If I put a really honking big number in for n, I get 2 to the 1 million. That's going to be 1 divided by an astronomically huge number. And so that's going to approach 0. Okay, which brings us to another property then. The limit of r to the n equals 0 if the absolute value of r is less than 1. Okay, so the limit of r to the n as n approaches infinity will be 0 if the absolute value of r is less than 1. Okay, All right, now we're going to take a look at infinite geometric series. Okay, so I'm going to bring you back to 20-1. We're going to go on a little trip down memory lane. Hopefully it'll be good memories for you all. Remember from grade 11, okay, you were given this formula, and essentially this is a summation formula for a geometric series. Okay, so S of n equals T of 1 times r to the n minus 1 all over r minus 1, where r can't be 1. Now it says determine the sum of the first 10 terms of the sequence. Okay, so essentially we're just saying, hey, give me S of 10. So I know my first term is 6. I know my r value is a half, because to go from 6 to 3 to 1.5, I'm multiplying by half each time. And I know that my n value, I already said that, is 10. Did I say that already? Sorry. So n is 10, just for clarification. N is 10, T of 1 is 6, and r is a half. Okay, so plug all that in and solve. Pause me first. Okay, so we're looking at this. Okay, and as we go to simplify this, we end up with, so 1/2 minus 1 is negative a half. Okay, so then what I did here, I'm just switching colors, 6 divided by negative a half would give me negative 12. That's where that comes from. Okay. All right. Now, the next thing I did was I said, hey, let's factor out a negative 1. Okay, so what I did was I took out a negative 1 from here, which caused that to be positive, and it changes the signs of this guy. So that's why my 1/2 to the 10 is now negative, and my 1 is now positive. Okay, so I factored out a negative 1. Okay, cool. Why? Why, Santa Claus, why? Okay, what happens, this is what I want you to think about now. What happens to 1 over 2 to the n as n gets bigger and bigger and bigger? Well, that was the property we just talked about. 1 over 2 to the n is going to become 0. So the way I've written this fella approaches 0. Well, if that approaches 0, I end up with 12 times 1, which is just 12. Yes? Okay, stay with me. If that didn't make sense, it's gonna in a minute. Okay, so the fraction would approach 0. So what are we saying? This is called, now this word you should know from 20-1. This is called a convergent series. We talked about a convergent and divergent, okay? Divergent means you got bigger and bigger and bigger, so it diverged. The sum just getting carried away from each other, okay? That's not what this guy is. This guy is a convergent. Convergent means it's coming together, okay? Because all of the partial sums will converge to, in this case, 12, okay? So when it's a convergent geometric series, there is a sum. When it's a divergent geometric series, there is no sum, okay? All right, this is a quick method for simple geometric series. They can be more complicated than what we're going to deal with, to see if the series converges or diverges. So let's go back to that general sum. We're going to take a look at this guy one more time. Okay, so this is just the equation that I started you off with for the summation of a series, a geometric series. Okay, but what I want to do is I want to use this now to show you how we actually build that geometric, the infinite geometric series that we just gave you in 20-1 and said, oh, here's a formula, use this. We're going to take this from a calculus perspective and we're going to derive that formula, okay? Okay, so here we go. Nothing's changed. I just wrote the formula there. But now, just like I did the first time, I'm going to factor out this, a negative 1 from here, okay? So that's going to become negative, this is going to become negative t1, and then this will become 1 minus rn, r to the n. And then at the same time, I'm going to factor out a negative 1 from here as well, okay? So that'll become 1 minus r. Okay, now, if you paid attention to that, if I factor out a -1 and I factor out a -1, those -1s will actually divide each other out as well. Okay, so here I went and factored out a -1. And so now I'm left with t of 1 over 1 minus r. So just to clarify, those are gone. I'm left with this guy times that guy. Okay. Okay, but what happens, oops, sorry, I thought I had my mouse back. What happens if the absolute value of r is less than 1? Now remember, you may be saying, oh, but you're forcing this to happen. Well, no, I'm not. If the absolute value of r is less than 1, that's convergent. Remember, we can only do this if it's convergent. Okay, and convergent means that I have to be getting smaller each time, which means my r value has to be a fraction of some sort. Okay, so if the absolute value of r is less than 1, I get, say, like whatever, say it's 1/2 to the n, right? And so that's the property we've been dealing with the last couple of slides, that will approach 0. So this ends up being 1 minus 0, which is just 1, which means your take-home message here is when the absolute value of r is less than 1, when I have a convergent series, I'm left with this. And that is the infinite summation that we gave you in grade 11. Okay, that's where that formula comes from. It really is derived from this guy. Okay, that's like really, really cool. I know you're sitting at home right now and like your heart is just racing so fast because you're so excited about this. Okay, it's good. It's good. Okay, just let me clear my drawings there. Okay. Okay, so I end up with t of 1 all over 1 minus r. Okay, so we'll do a quick summary here. If the absolute value of r is less than 1, the geometric series is convergent and has a sum of t of 1 over 1 minus r. If the absolute value of r is greater than 1, the geometric series is divergent and the sum will go to infinity. So we can't actually calculate the sum. Okay. All right, so determine the sum, if possible, of the following series. So I'm looking at 4 going to -4 over 5, going to +4 over 25. How am I doing that? I am multiplying by -1/5 each time. Okay, so my r value is -1/5. That is an r value. The absolute value of r is less than 1 here. So I do have a convergent series. So I can just go and plug it all in. 4 divided by 1 minus r. So 4 divided by, that would be 5 over 5. So that'd be 4 divided by 6 over 5, which ends up being 4 times 5 over 6, which ends up being 20 over 6, which reduces to 10 over 3. Okay, just in case you're wondering where that 10 over 3 came from. I'm sure you guys are fine with what just happened, but just in case you're not, 4 divided by 1 plus 1 over 5 is 4 divided by, I called that 5 over 5, so that's 6 over 5. So I've got 4 divided by 6 over 5, which is 4 times 5 over 6, which is 20 over 6. Okay, I got to get a new marker. Hopefully you can see that okay. Okay, chucking this guy out. Watch. Gone. Okay, so the sum of infinity for this guy is 10 over 3. All right, try this guy. 4, then -6, plus 9, minus 13.5, plus blah, 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 blah. I want you to see that those numbers are actually getting bigger each time. If those numbers are getting bigger each time, this is a divergent series, so there's not going to be a sum. But I want you to calculate the r value. It'd be -6 over 4, which would reduce to -3 over 2. Okay, so then you want to conclude the series is divergent and there is no sum. Okay, cool. For what values of x is the series the summation of x plus 1 to the n, where n is 1 to infinity, convergent? What is the sum of the series? Now, we should just have a little conversation here first, because this may be the first time you see sigma notation. The sum of an infinite series may be written in sum or sigma notation. Now, what this essentially is this guy is the formula you're using. And then this essentially says we are going to plug in 1, plug in 2, plug in 3, plug in 4, all the way to infinity. And then this symbol here means it's a series, so we're going to add it up. Okay. All right. So that means you've got x plus 1 to the 1, x plus 1 to the 2, x plus 1 to the 3, and so on and so forth. Okay. Now, we are looking for what x values would allow this to be convergent. Now, if I want it to be convergent, I know the absolute value of r has to be less than 1. Okay, I know t of 1 right now is x plus 1, because that's my first term right here. Okay, and then how do I go from here to here? Well, I multiply by x plus 1. How do I go from here to here? Well, I multiply by x plus 1 again. So my r value right now is x plus 1. Okay, now, if I want it to be convergent, then I know that the absolute value of r has to be less than 1. So either r is less than 1, and if that was the case, I'd say x plus 1 is less than 1, which means x has to be less than 0. Okay, because r is x plus 1. I just replaced r with x plus 1. Or because it's absolute value, that also means negative r could be less than 1, which means negative x plus 1 could be less than 1. A reminder, however you do this, at any point in time when you divide or multiply by a negative number, you have to flip the inequality. So that becomes x plus 1 is greater than negative 1, and that means x has to be greater than negative 2. So in order for this series to be convergent, I have to have an r value somewhere between negative 2 and 0, is what this just told me. Okay, so my r value has to be between, my x value, I shouldn't have said r value there. My x value has to be between negative 2 and 0. Okay, all right. So then it says, what is the sum of the series? Well, the sum of the series would be x plus 1 over 1 minus r, where r is also x plus 1. So I end up with x plus 1 over x. And that would work as long as, again, my x value is somewhere between negative 2 and 0. Okay, it would not work outside of that x value being negative 2 to 0, because outside of that negative 2 to 0, my series would become divergent, not convergent. Okay. All right. Excellent. So that's where we leave off. And that's the end of this unit. So that's your mission for this lesson, but then there's also a review in your book. And then as far as the video lessons go, we will come together again when we start chapter 2, unit 2. Yeah, so I'll see you then. Okay, remember, if you have any questions, please, please, please make sure you're getting in contact with me. Okay, that's what I'm here for. Take care, guys. Bye.